Welcome to The Explainer. If you're a lighting designer or an engineer, you know that just picking a white light is, well, it's not that simple, is it? Today, we're going to pull back the curtain on the hidden science that really determines a light's impact on the environment. And I'll tell you right now, it goes way beyond just lumens and color temperature.
All right, let's kick things off with a real head-scratcher. Picture two streetlights. To your eye, they both look perfectly white. But one of them could be a major contributor to sky glow, messing with local wildlife, while the other is, much gentler on the environment. How can that be? They look the same.
So here's the thing. The answer isn't just about how bright the light is. It's all about what's inside that light. The secret, the real story, is hidden in its spectrum.
So how are we going to crack this case? First, we'll establish why spectrum is the absolute key. Then, we're going to learn how to read light's DNA, which is called its spectral power distribution. After that, we'll see how different technologies cook up their unique light recipes. We'll zoom in on the real problem child, blue light. And finally, we'll tie it all together with some practical design tips for a better, darker night sky.
Okay, first up, why does spectrum even matter? This is where we need to do a little mental reset. We have to stop thinking just about how light looks to us and start thinking about what it's actually made of.
Think of it like this. Every single light source, the sun, an old-school incandescent bulb, a cutting-edge LED, has its own unique fingerprint. It's a specific recipe, a mix of different colors and wavelengths that all blend together to create the light we see. And that fingerprint, not the color we perceive, is what actually interacts with our atmosphere and with all living things.
Okay, so we've got this fingerprint idea down. Every light has one. But how in the world do you actually read it? Well, to do that, we engineers have a really critical tool that lets us see the very DNA of light. First, a super quick refresher. The visible light we see is just a small slice of a much bigger spectrum. On one end, you've got the short, punchy wavelengths of violet and blue light. And way over on the other end, you've got the long, stretched-out wavelengths of red light. And of course, every color of the rainbow is in between. And that brings us to the hero of our story today, the spectral power distribution, or SPD for short. You're looking at a graph that is basically a precise map of a light source. It tells us exactly how much energy that light is putting out at every single color, every single wavelength. It is literally its DNA profile.
So when you look at one of these graphs, it's actually pretty straightforward. Along the bottom, you have all the colors laid out, from blue to red, and going up the side, you have the amount of power at each of those colors. That curve you see, that's the light's unique recipe. And that recipe tells us so much more about its environmental impact than just its brightness or its overall color ever could.
Okay, so we know what an SPD is. Now for the fun part. How do the different light bulbs we use every day actually make these different light recipes? Now, you've definitely heard of correlated color temperature, or CCT. It's measured in Kelvin, and it's a handy shortcut. It gives us the general vibe of the light. Is it going to feel warm and cozy like a candle, or cool and crisp like the midday sky? But, and this is important, it's just a perception. It's not the whole story.
And here's where you can really see the difference in technology. An old incandescent bulb is simple. You heat a piece of metal, and it glows. That creates a really smooth, continuous spectrum, a nice, even spread of all the colors. But a modern LED, it's a different beast. It starts with a really powerful blue LED, we call it the pump, and then it uses a clever coating of phosphorus to convert some of that intense blue into other colors like yellow and red. The result is a much spikier spectrum, and you always get that sharp, telltale peak of blue.
Well, let's put some real-world numbers on CCT. Down around 2700 Kelvin, that's what we call warm white. It's that cozy, relaxing glow you get from an old light bulb. Jump up to 4000 K and you've got neutral white. It's more balanced, what you find in a lot of offices. Then you get up to 6500 K, that's daylight white. It's very crisp, very energetic, and it's got a very obvious bluish tint to it.
So what's the big connection back to our spectrum? It's a direct, unavoidable relationship. As the CCT number goes up, the amount of that short wavelength blue light in the mix goes up a lot. That cool or daylight look isn't just a feeling. It's the direct result of having a ton more high-energy blue light in the recipe.
So we've established that higher CCT lights have more blue light. But the really important question is, so what? Why should we care? What's the big deal with this one part of the spectrum when we're talking about the nighttime environment?
The plot thickens right here, at this specific number, around 450 nanometers. This is the wavelength of that powerful blue pump that acts as the engine for most white LEDs. It's what makes them so efficient, but it's also ground zero for the environmental problems we're seeing.
So why is this null peak such a troublemaker? Two big reasons. One is physics, the other is biology. The physics part is that short wavelength light bounces around in our atmosphere like a pinball. It scatters everywhere, creating that ugly orangish dome of sky glow that blots out the stars. The biology part? Well, for millions of years, the internal clocks of almost every living thing have used blue light as the signal for daytime, wake up. When we flood the night with it, we're basically screaming wake up to every animal, insect, and even plant, and it messes everything up.
And you can see the effect plain as day right here. The cool, blue-rich light scatters all over the place, creating a massive dome of light pollution. But the warmer light, with way less blue, it scatters less. The light stays down on the ground where you want it, and the sky stays dark.
And we're not just talking about losing our view of the stars here. The damage goes way deeper. For a moth, that light can be a fatal trap. For a bird migrating thousands of miles, it can throw off its internal compass. For a baby sea turtle, it can mean crawling towards a parking lot instead of the ocean. For countless nocturnal animals, it disrupts their ability to hunt, to mate, to survive. It's a problem that echoes through the entire ecosystem.
Okay, that's the problem. And it's a big one. But the good news is we are engineers and designers. We have the tools to fix it. So let's talk about the solutions. How we can use this knowledge to engineer a much better, much healthier night.
Here's your playbook, your 4 golden rules for responsible design. Number 1, always get the SPD data. Stop relying on CCT alone, look at the actual fingerprint. 2, specify your light based on its spectrum. You want to actively choose lights that have as little energy as possible below 500 nanometers. 3, as a simple rule of thumb, stick to 3000 Kelvin or lower for almost all outdoor lighting. And finally, number 4, remember that spectrum is only one part of the puzzle. You have to pair it with good old-fashioned lighting design, full shielding, dimmers, timers, using only the right amount of light, exactly where you need it, and only when you need it.
So let's boil this all down. CCT is just a perception, a vibe. The SPD, that's the physical reality. And that's what tells you the real environmental story. That blue peak in LEDs isn't some accident. It's an engineering feature that we have to actively manage. The real goal here is to find that sweet spot, that balance between what we need as humans and our responsibility to the environment.
It all comes down to this simple idea. Think of good lighting like a 3-legged stool. One leg is safety and performance for people. The other 2 are environmental responsibility and protecting the night. If any one of those legs is too short or too long, the whole thing falls over. It has to be in balance.
So now that you understand the spectral power distribution, you're not just picking a white light anymore. You are choosing its fingerprint. You're choosing its DNA. You are now equipped to make choices that don't just light up our world, but actually help protect it.